Okay, so we're now on to looking at normal reaction force, and this example is to do with a lift, which I think is a brilliant context in order to look at reaction force. Okay, and this idea behind opposite and equal forces in a bit more detail. So in this question, we are given the mass of the person, and they said they're standing in a lift. We are not given the mass of the lift, so we can't look at the forces acting on the lift, just on the person. So in fact, I think what I was talking about with the opposite and equal forces is maybe something the next example we'll have a bit more looking at. So I've got a lift with a person in it, touching the ground maybe, and the person's got a mass of 76 kilograms. I can't really fit that in there, but that means they've got a weight of 76 g. And it says find the magnitude of the normal reaction force exerted by the floor onto the person. So reaction force by being in contact with a surface effectively. So currently my person is not in contact with it. So that is what they feel from standing on the bottom of the lift. So they feel that kind of pushing up force. And that's what we want to find in these three scenarios. So I'm not going to put a direction of motion onto this yet because it might be different in all three parts of my question. So in part A, it says that lift is moving upwards. So we're going to take upwards as positive. So my forces are going to be R, take away 76g, forces up, equal to mass 76 times by acceleration of positive 2.6. And I'll rearrange that once I track down a calculator. So it'll be 76 times 9.8 plus 76 times 2.6. I think that's 900 to 3 sig fig 942 newtons. Right, let's have a look at part B then. So now it says it's moving downwards with an acceleration of 2.6 meters per second squared. So this time we've got F equals ma down. So we've got 76g. Take away the reaction force equals 76 times 2.6 again, but obviously rearranged differently. So I get the R moving on to the right, so it's going to be 76g take away 76 times 2.6. So that's 547 to 3 sig fig newtons. And the idea about feeling heavier in a lift and lighter in a lift in certain situations when you're moving upwards and downwards, this idea comes in now, which is interesting. So the last one we're moving downwards, so I'll keep downwards as positive direction, but the acceleration this time is negative, so it's going to be negative. So it's going to be 76 times negative 2.6. So we're going to have 76g minus reaction force equals to that. But I think if you rearrange this, you get the R moving to the right and this moving to the left, which I think gives us that. And if you put it in your calculator, you get that same 942 newtons. Okay, so this feeling that you get of being maybe heavier if you are on your way up in a lift and it's accelerating, or if on the way down on the lift and it's slowing down. Whereas if you're on the way down and it's accelerating, you may be feeling lighter. So these kind of ideas are quite nice. So the idea that reaction force equals to, so R equals mg effectively, is maybe debunked nicely in this reaction force. So that is only true if the object is not accelerating. In a lift, it's a good example of reaction force where we are accelerating. Okay. Obviously, you can have a lift that's not accelerating as well.